High-quality stainless steel sheets or coils are selected as the base material, chosen for their corrosion resistance and strength. The steel sheets are cut into specific shapes or blanks using a hydraulic shear machine, preparing them for further processing. The cut stainless steel blanks are passed through precision rollers to reduce thickness, improve surface uniformity, and enhance mechanical properties, ensuring consistent material quality for forming processes. The rolled material is inspected and prepared for shaping. Excess or uneven edges are trimmed using specialized cutting machines to create smooth, uniform outlines, ensuring accuracy and safety in the final cutlery shape. Removes surface imperfections and shapes the cutlery, preparing it for a smooth, refined, and visually appealing finish. Cleans residues like oil, dust, and metal particles from grinding, ensuring a contaminant-free surface for the next steps. In this step, components like knife blades are precisely welded to handles using high temperature or laser welding, ensuring strong bonding, structural integrity, and seamless appearance in multi-part cutlery. Edges, particularly on the sides, are ground down for consistency, safety, and better aesthetics. The cleaned and trimmed blanks are shaped into their final utensil forms using high-pressure stamping machines, which press the metal into detailed molds with precision and consistent dimensional accuracy. Robotic systems polish the utensils to a uniform finish. Skilled workers perform detailed hand polishing using abrasive belts, wheels, or cloths to refine areas that machines may miss, especially around complex curves, edges, or joints. This step enhances the smoothness, luster, and visual appeal of the cutlery. Manual polishing also allows for quality control by touch and sight, ensuring each piece meets high aesthetic and functional standards before moving to final cleaning and inspection. After polishing, the cutlery undergoes thorough cleaning using ultrasonic baths, detergents, or high-pressure water to remove polishing compounds, dust, and residues. This ensures a spotless, hygienic surface ready for final inspection and packaging. Each cutlery piece is carefully examined for defects, surface finish, and structural integrity. Approved items are then sorted, counted, and securely packaged for safe transport and customer satisfaction. In the die shop, skilled technicians design precise tooling, then use advanced CNC machining centers to cut detailed cavities into steel die blocks, ensuring accuracy and repeatability for wax pattern production. In this step, high-quality wax is injected into the machine die using precision wax injection presses. Temperature, pressure, and cycle time are carefully controlled to ensure complete filling and solidification. This results in a wax pattern that perfectly replicates the die cavity's intricate details. Each wax pattern is thoroughly inspected to ensure dimensional accuracy and surface quality before moving forward. Multiple wax patterns are assembled onto a central sprue, forming a tree structure ready for automated ceramic shell dipping. Wax trees are repeatedly dipped into a ceramic slurry, then coated with fine sand or refractory material. After each dip, the coating is allowed to dry in a controlled environment to ensure uniform strength and thickness. This cycle is repeated multiple times to build a durable shell mold capable of withstanding high temperatures during metal casting. The ceramic molds are heated to melt out the wax, then carefully stored to prevent damage and reduce scrap before casting. The Bruker Q2 metal analyzer precisely measures the chemical composition of metal alloys, ensuring each melt meets strict specifications for strength, durability, and performance before being poured into molds. Molten metal is poured into preheated ceramic molds by skilled operators wearing protective gear. Metal temperature is carefully monitored to ensure optimal flow and fill. This critical step solidifies the final shape and structural integrity of the casting. After cooling, ceramic molds are broken off using pneumatic hammers, and cast parts are separated from the tree for processing. Castings are cleaned, ground to precise dimensions, finished to specifications, and thoroughly inspected to ensure quality and customer requirements. Final castings undergo CNC machining operations such as milling, turning, and drilling to achieve exact tolerances and functional specifications. The rib plate flipping robot is an automated system designed to safely and efficiently rotate heavy rib plates, improving workflow, reducing manual labor, and ensuring precise positioning for welding operations. Plasma cutting uses a high-velocity jet of ionized gas to melt and cut through electrically conductive materials with precision, producing clean edges ideal for intricate and high-speed fabrication tasks. Flame cutting, also known as oxy-fuel cutting, uses a combination of oxygen and fuel gases to heat and sever thick carbon steel, offering a cost-effective method for heavy-duty material processing. The rib plate assembly and welding robot automates the alignment and welding of rib plates onto structural components. It ensures precise positioning, consistent weld quality, and high efficiency, significantly reducing manual labor while enhancing overall structural strength and assembly speed. The web plate welding robot performs automated welding on vertical web plates, ensuring uniform weld seams, enhanced structural integrity, and high production efficiency for critical load-bearing sections of crane beams. The double girder main beam inner seam welding robot workstation is a highly specialized, automated welding system designed for precision welding of the internal seams of double girder main beams. This workstation utilizes advanced robotic arms equipped with intelligent sensors and adaptive control technology to achieve consistent, high-quality welds in tight and hard-to-reach areas. It ensures deep weld penetration and uniform fusion along the entire length of the inner seams, which are critical for the structural integrity and load-bearing capacity of overhead and gantry cranes. The system minimizes welding distortion, reduces human error, and enhances production efficiency. Its fully automated operation also lowers labor intensity, shortens manufacturing cycles, and guarantees superior product consistency, making it a key component in Henan Mine Crane's advanced manufacturing process. The double girder production line gantry type overhead crane beam welding special machine enables continuous, high-precision welding of large crane beams, ensuring alignment accuracy, uniform welds, and increased efficiency across the production line. The double girder trolley frame overall boring and milling process involves high-precision machining of the entire trolley frame to ensure exact dimensional tolerances and proper alignment of mounting surfaces and connection points. This step is critical for the smooth operation of the crane's trolley system, as it directly affects gear meshing, bearing placement, and overall structural stability. Using advanced CNC boring and milling machines, Henan Mine achieves consistent accuracy, enhances component lifespan, and guarantees optimal performance under heavy-duty industrial working conditions. Drum annealing for stress relief treatment involves heating welded components to a controlled temperature and slowly cooling them, effectively reducing internal stresses, preventing deformation, and enhancing the structural stability of crane parts. Sand mold production is the first and most crucial step in the casting process. At our facility, we utilize advanced F1 molding machines along with horizontal automatic molding machines, AMF, and vertical molding machines, SM, to ensure precision and consistency. These machines compact special sand mixtures into pre-designed patterns to form strong, detailed molds. This automated process improves accuracy, reduces human error, and enhances productivity, enabling the creation of high-quality molds suited for complex and thin-walled castings. Melting is performed using a furnace called a cupola. Fuel in the form of coke is burned to melt raw materials and prepare them for casting. Molten metal, heated to over 1,500 degrees Celsius, is carefully and swiftly poured into the prepared sand molds using ladles or scoops, ensuring a smooth fill without turbulence or air entrapment. After the molten metal cools and solidifies within the mold, the sand mold is broken apart using mechanical or manual methods to release the casting and separate it from the sand. The separated casting undergoes surface cleaning using a shot blasting machine, which propels high-speed steel shots to effectively remove residual sand, scale, and impurities, ensuring a clean, smooth finish. Each casting is carefully inspected for damage or defects. During finishing, any excess material, such as flash or parting lines formed along the mold joints, is carefully removed using specialized grinding and trimming machines to achieve a precise, smooth surface. In the machining process, high-calorie gas burners are precisely shaped using lathes for rotational cutting, while Morning Glory-style burners undergo drilling operations to form accurate holes and component fittings. To protect against corrosion, each casting is coated with a specialized anti-rust paint tailored to the product's intended use. This coating enhances durability, appearance, and longevity under various environmental conditions. Each gas valve is meticulously tested using a precision pressure gauge. This process ensures airtight sealing and verifies that there are no gas leaks, guaranteeing safety and optimal performance in operation. In the welding stage, steel components are fused together using high-precision automated MIG welding systems. This ensures consistent, high-strength joints critical for heavy-duty applications. Advanced sensors and robotics monitor weld quality in real time, reducing defects and ensuring each rim meets strict durability standards. The process is optimized for efficiency, repeatability, and structural performance under extreme operating conditions. Rim rolling involves forming the circular steel rim from flat-rolled steel sections using high-pressure rollers. This cold-forming process ensures uniform thickness, precise dimensions, and superior structural integrity. Automated rolling machines shape the rim to exact specifications, minimizing material waste and improving concentricity. The result is a strong, balanced rim capable of withstanding demanding off-highway and agricultural use. High-pressure washing removes oils, debris, and contaminants, ensuring a clean surface for coating, painting, and final assembly. On assembly line, cleaned and formed rims are fitted with discs, valves, and other components. Automated and manual operations ensure precise alignment, torque, and quality checks, delivering fully assembled steel wheels ready for painting and final inspection. Stainless steel sheets are deep drawn into cylindrical bottle shapes. Extruded tube stock is essential for manufacturing narrow-profile vacuum products, such as slim bottles and compact flasks. These tubes are produced by forcing stainless steel through a die, creating a seamless, uniform cylinder with consistent wall thickness. This method ensures strength, durability, and precision, which are critical for maintaining vacuum insulation. Using extruded tube stock also reduces the need for welding, minimizing weak points and improving the overall structural integrity of the final product. Press fitting the vacuum tubes as shown on the vacuum machine. Automatic welding on the base of tube. Manual welding. Removes air between walls to create long-lasting thermal insulation. The grinding, buffing, and polishing area is where each stainless steel product receives its smooth, refined finish. Skilled technicians use specialized equipment to grind away weld marks, surface imperfections, and rough edges. Buffing wheels and polishing compounds are then applied to create a uniform, glossy surface that enhances both appearance and hygiene. This meticulous process not only improves the visual appeal of the mugs, tumblers, and flasks, but also prepares the surface for any printing or branding that follows. Applies custom logos and designs using durable, heat-resistant ink. In the hotbox process, sand pre-coated with thermosetting resin is injected into a heated metal core box. The heat activates the resin, causing the sand to rapidly cure and harden into the desired core shape. These cores are used to form complex internal passages, offering high dimensional accuracy, strength, and resistance to thermal deformation during casting. In the cold box process, dry silica sand is mixed with a two-part resin binder system, typically polyurethane-based. This mixture is blown into a metal core box, where it conforms to the desired shape. A reactive gas, usually amine vapor, is then injected into the cavity, triggering a chemical reaction that rapidly hardens the core at room temperature. This method produces strong, precise cores with excellent dimensional stability, and is ideal for high-volume production of intricate engine block features. In the V6 engine block casting process, installing heated liners and accurately assembling sand cores are crucial for ensuring dimensional precision and metallurgical quality. Cylinder liners, typically made of cast iron or steel, are preheated to a specific temperature, usually between 150 degrees Celsius and 300 degrees Celsius before installation. Preheating the liners serves several purposes. It reduces the temperature differential during casting, minimizing thermal shock, and it promotes better metallurgical bonding with the surrounding molten metal, improving the structural integrity of the engine block. Once the liners are heated, they are carefully placed into the core assembly fixture, aligning them precisely to match the cylinder bore layout. High positional accuracy is essential to maintain the correct bore geometry and wall thickness during casting. Following liner placement, the pre-made hot box and cold box sand cores are assembled into the mold. These include water jacket cores, crankcase cores, and other internal passage cores. The cores must be accurately positioned and securely fixed using mechanical supports, adhesives, or ceramic glues to prevent movement during the casting process. Misalignment or instability can lead to severe casting defects. This assembly forms the complete cavity that defines the internal and external features of the V6 engine block. Low-pressure casting is a precision method used to produce high-quality V6 engine blocks. In this process, molten aluminum, or other metals, is contained in a sealed furnace below the mold. A low-pressure air supply, typically 0.5 to 1 bar, is applied to gently push the molten metal upward through a riser tube into the mold cavity. This bottom-up filling minimizes turbulence, reducing the risk of gas entrapment and oxide formation. The controlled flow results in a dense, uniform casting with fewer defects and improved mechanical properties. The process allows for excellent dimensional accuracy and repeatability, especially important for complex engine blocks. After solidification, the pressure is released, the casting cools, and the mold is removed for core shakeout and further processing.